Mehmet Dogan. I'm going to talk about first principles methods in solid state physics and how we do calculations of real systems, including large systems. Oh, thank you. Okay. The framework I use in my work is called the density functional theory, and I'll talk about what that means. So we start with the Schrodinger's equation, which is what governs the electrons in a system. It's a simple differential equation for a single electron. You have the kinetic energy term, the potential energy term, you have a wave function, and it's an eigenvalue problem. The problem is when you have multiple electrons, it becomes a many-body problem, and it quickly becomes intractable. The many-body quantum mechanics is extremely difficult. So when quantum mechanics was developed early last century, people realized, and Dirac formulated this, that we have developed a mathematical theory governing the systems of small size, such as electrons. But we need practical methods of applying quantum mechanics so that we can solve the actual systems that we see around us. What I focus on is the density functional theory, which was developed in the 1960s by Kohn and Sham. It essentially consists of two theorems. The first one says the ground state properties of a many electron system are uniquely determined by its electron density. So rather than dealing with multiple electron wave functions, and in solid systems, jillions and jillions of wave functions, we can work on the scalar function NFR, right? So that determines the properties of the system. And the second theorem says the ground state energy can be variationally obtained by variational calculus, and the correct NFR minimizes the energy function. And the variational calculus leads to these equations we call Kohn-Sham equations. And now these equations look quite similar to the Schrodinger's equation. So here we have pseudo wave functions phi. So they're, for practical purposes, they're wave functions. We have, again, a Laplacian, and then we have three parts for the potential. The first term is the Coulomb repulsion between the positive charge and the between the nuclei. The Hartree term is the average electron-electron repulsion, and then this functional for the exchange correlation potential includes essentially all the many-body interactions between the electrons. So we can further simplify the problem by reducing the number of electrons. If you have taken physics or chemistry or familiar with valence electrons, so we can use this concept, right? For example, in silicon, we have for a silicon atom 14 electrons, but the first 10 electrons don't contribute much to chemistry or bonding or solid state physics, right? So instead, we can include only the valence electron, but not the core electron. So we combine the core electrons with the nucleus of the atom. And instead of solving for our wave functions with the same level of precision everywhere, we solve within the space between the ions. So we assign a certain radius to each ion, and we only solve for between the space between include ions, and within the ions we assign a simpler solution. So this is called the pseudopotential approach. So rather than nuclei, we have ions, we have fewer electrons, and we have the electron density. Okay. So density functional theory has been very, very successful in practical applications. In 1998, Walter Kohn received the Nobel Prize in chemistry. He said that DFT makes two kinds of contribution. The first is in the area of fundamental understanding. So by solving for the full electronic structure of our systems and materials or in chemistry, we can understand the fundamental properties better. And the second contribution is practical. So we're able to determine the electronic structure of systems that we were not able to before, and that helps us guide applications. So today I'm going to focus on what we call the real space method. And to get there, we need to realize that we can represent the phi functions, the phi sub I functions, using various bases. One example is atomic orbitals. So for each wave function, we can express them as a linear combination of atomic orbitals. That's an approach. Another approach that's actually the most common one is using the reciprocal space and making a grid in the reciprocal space. So by reciprocal space, we mean sometimes the K space or the wave vector space, where especially in solid state systems where we have periodicity, we can quantify the periodicity of each of our functions in the spaces, and that periodicity corresponds to a point in the K space. And the symmetry reduced version of that is called the Blue zone, and then that allows you to probe the electronic states of the system in a systematic way. For example, this is a band structure, or also called band dispersion. So it shows you where the energies are for each type of periodicity in your system, and you represent this x-axis as a path in the Brillouin zone. Yeah.
There was what you said, Kohn says that it was used to work with truncated Hilbert spaces. What is a truncated Hilbert space?
The Hilbert space in the code?
I know what a Hilbert space is, but truncated.
Oh, here in the quote?
Yeah.
Okay. I didn't read this in a while.
I expect that this, when you have a Hilbert space, you have an infinite basis.
Yeah.
And probably it's cut chatting.
Yeah.
The basis to something finite, I guess.
A truncated Hilbert space of single particle orbitals. Yeah. So that's actually a good point to probably touch upon. So we can have infinitely many of these eigenstates, right? And in real systems, electrons fill up these levels, and because electrons are fermions, they can only fill up essentially one per state. So we fill them up, and then we're done, and everything else is empty. Those empty states are also important, but they're not important up to infinity. So in real calculations, we will cut off the energy at some level. So our Hilbert space is truncated. Okay, so as I said, the reciprocal space grid is very useful in solids, but what we focus on today is real space, meaning that we make a grid in the real space of the system and solve these equations in real space. Okay, so there are some advantages to real space. For example, in the real space, the sparse matrix vector multiplication is more efficient compared to the K-space. We are able to implement the finite difference method for the Laplacian operator in a straightforward way as well. So that's easy implementation. So it provides the best scaling with the system size compared with other bases so far. So in 2008, there was a short paper describing the trends in different ways of solving the electronic structure problem. As you can see, the exact treatment where you exactly solve the many-body problem, it is scaling up extremely slowly. So the number of atoms that you can probe in this way is not even 10, right? And then there are various other methods. And if you look at DFT and if you just extrapolate to where it hits 100,000 atoms, you expect that around 2035. But we developed certain algorithms and methods to improve the scaling of our DFT, and we achieved this in 2023, actually. We were able to solve a 100,000 atom system in 2023. I'm going to talk about how we did that. So there are problems with traditional eigensolvers. They converge slowly, difficult to parallelize. I'm generalizing, but just in general, and they are not able to the same extent as you would like to take advantage of good starting points. And we are interested in eigenvalues near the bottom. Farther from the bottom tend to make the problem harder. So my colleagues developed before my time this or implemented Chebyshev-filtered subspace iteration, which essentially works by enhancing the lower parts of the spectrum and suppressing the higher parts of the spectrum. So you randomly generate initial subspace, apply a filter, orthonormalize the subspace, and then obtain eigenpairs via the Rayleigh-Ridge method. And this is in a quick summary how this method works. In terms of comparisons with other methods, you can see the Chebyshev filtering method for the same system performs 5 or 6 times better than the next best method we have. In terms of the computational cost as a function of states, so we have, if you break down the number of grid points, actually we have the number of grid points and the number of states that go into the scaling. And they scale with each other. So roughly these are equivalent, but if we can find a way to also improve the scaling with respect to states, that would be helpful. So as you can see, these are silicon quantum dots going from about 2,000 atoms, 4,000 to 50,000. And the steps with the that scale with n squared or n cubed, they dominate in terms of computation costs. So to tackle this, I helped develop a method called spectrum splicing. So the idea here is, for example, if you have the density of states in this plot, meaning how many states you have per energy interval, right? These are the values that we're trying to determine. It's usually made up of sections or certain blobs, and if you could only focus on these sections one at a time, you would reduce the number of states by a lot. So we would be able to slice up our spectrum. So rather than doing the orthonormalization and the Rayleigh-Ritz steps for the whole spectrum, we do them by slice. In practice, we found that this method is worthwhile if the number of our slices is large, and that works for larger parallelization, larger numbers of processors. For small number of slices, it's not worth it. So it's important to implement for larger systems because it can save up to it can take your time about reduce it by 2/3 essentially.
And will you say something about how do you decide and how many slices you're gonna take?
Yeah. So that's going to be system dependent. So it's better if you have an idea of your spectrum to begin with. So here in this study, I'm focusing on silicon clusters. So we have a pretty good idea of the result, which allows us to set up these filters very well. So if you don't have any idea, you would probably do a crude calculation without any slicing to get a rough idea and then turn on the slicing.
So are these amorphous structures or crystalline?
They're crystalline, but they're finite. They're spherical. So they're 0D as we call it because it's not periodic actually, but in the structure it's crystalline. All right. So the next set of ideas is about partitioning the grid. Okay. I think I'm going to have to change my pointer. I had a different one. Should be good. Okay. So we need to find a way to partition the grid in 3 dimensions such that every grid point can be assigned to a process, right? So we need to go from a 3-dimensional set of grid points to 1 dimension. So using space filling curves is useful because it's a 1D representation of 3D. It has self-similarity and good locality, meaning you don't jump from this end of the domain all the way back to this end. It's continuous. And we are using Hilbert space filling curves that are easy to implement. So the idea here is you generate these points and then connect them in this systematic way, and you can increase the number of generations and decrease your grid spacing. So you end up with a pretty dense Hilbert space curve that travels all throughout the real space domain, finite domain. So this is better for a load of the different processes as well, compared to Cartesian ordering. We also use something called blocks. So this method is called blockwise filter. So the simple Cartesian ordering would look like this. You would go, all the way up, jump back down, go all the way up, and so on. This would be the blockwise simple Cartesian. So you do this, but in blocks. The Hilbert space filling curve would look like this, and then this would be the blockwise version. If we look at the performance for the same problem, the speed up compared to the simple Cartesian ordering is pretty significant, especially if you implement blockwise Hilbert. So as you can see, it speeds things up by about 6 times. So these all helped us get to better scaling. It also scales almost ideally, so it is very hard to beat in terms of the speed that you get. So at UT Austin, I developed and implemented these features in this code called Parsec. So Parsec is a full density functional theory implementation where you can download and start solving real density functional theory problems. You're my main collaborators there. And to test and prove the concept of the superior scalability of real space, we ran the largest self-consistent Kohn-Sham DFT calculation today. So we solved the electronic structure problem for more than 100,000 atoms. And then we did some further improvements and simulated a system twice as large as well. So that put us to nearly 1 million electrons. In terms of the results and the scale of the calculation, I like to show these plots. So we start with the 2000 atom quantum dot. And a quantum dot essentially looks like this. So it has the interior structure of silicon, but it is finite. It's a spherical system.
Is that a projection? The picture.
The picture?
Is it a projection
Of
of a 3D?
Yeah, it's the whole quantum dot from a certain angle with perspective turned on, I guess. Yeah. So I don't know exactly which one this is. This is probably one of the smaller ones, but I didn't generate the image for the largest one. No, that'll probably break my image generation software. So in terms of the size, the physical size of these nanodots, we go from 4 nanometers to 16. These are the supercomputers we run these on. The number of nodes. This is the grid spacing, meaning the spacing between grid points, right? So this is one of the advantages of real space, where in other types of density functional theory methods, you have to optimize different parameters, 2 or 3 different parameters. In real space, this essentially controls the convergence. So only by changing h, you can converge your calculation. As you can see, we had to go from 0.7 to 0.9 at a certain size because it was just getting too big. And this gave us the number of grid points going from 1.5 million to about 30 million. Number of states that are included in the calculation. And this is the number of SCF steps, number of self-consistent field steps. So we solve the Kohn-Sham equations iteratively, self-consistently, and we define a certain convergence threshold, which is pretty strict, and it only takes you less than 20 steps to get there in each one. And then this is the total time it took for each calculation in hours. Yeah.
For old people who haven't done the number of states in 20 years or something like that,
Yeah.
and you just give me a 30-second explanation what the states are.
Right. So these are the number of eigenstates that we're solving for, essentially.
Including the empty ones.
including the empty ones. Yes, yes.
So in your calculation, what kind of like a basis function is that like a atomic centered basis?
No, as I said, it's just real space.
Real.
It's just numbers assigned to the group points.
Group.
Yeah, yeah. Exactly. So the number of states, I mean, those of you that are interested in physics, it's for silicon, for example, for the 100,000, we have 4 electrons in the valence band. That means because each electron can have 2 spins, you need 2 states that are filled. So that's where the 200,000 states come from. And then we need some extra states, of course, to be able to simulate beyond the Fermi level. So the conduction band states are also included, but not too many of them.
Okay.
Yeah, of course. So this is what we call the density of states. So it's basically because we're literally finding every single eigenvalue. This is just a histogram and nothing else, nothing fancy. Right? So we're just plotting the number of eigenstates within a certain window as a function of that value, the energy. And this dashed line is what we call the Fermi level, below which it's all filled, above it's all empty if you're at 0 Kelvin. So what I like about this, if I go through every row, you can see the density of states becoming smoother. Right? And then as you reach the largest system we did, it's pretty smooth. And this is very interesting because this is what you find, the shape of this curve is what you find in the solid state when you have an infinite crystal of silicon. And these features of the density of states, for example, the singularity type feature, these reflection points and such, they're all of interest to physicists, and they're usually understood and explained in terms of the reciprocal space and the periodicity of wave functions. Here in this calculation, we have done nothing in the reciprocal space. Everything was in the real space. We still get these features, these exact same features. So it's interesting that they can be, obtained without any reference to the K-space. Yeah.
Yeah. Why did you use the word infinite? I think you used that word.
Yeah. So if you look at a solid state physics textbook, the methods that are discussed, the density of states, calculations that are done, etc., are for an infinite crystal. So usually we approximate large systems as infinite in solid state physics.
Okay, but you're not talking about a silicon quantum dot the size of the Earth or anything like that.
No, I mean in solid state physics, usually we just say it's too big to matter, but the surface is too far to change anything.
So it's like asymptotic or something.
Yeah, but let me show you the next plot. Maybe that'll be helpful. So, for example, the band gap, which is the difference between filled and unfilled energies, goes down as a function of the diameter of the nanocluster. And we fit this curve to this equation. And as you increase the diameter, right, it should approach the 0.46 eV value. And that means in our calculation, if we actually had an infinitely large quantum dot, we would expect this band gap. The reason the band gap changes quite dramatically with size is something called quantum confinement. So this is another physical phenomenon we obtain directly from the calculation, right, without having to introduce it separately. So quantum confinement says if your wave functions are confined within a certain space, they're broadened. And this is what we observe. Yeah.
What are the two curves there?
The blue curve is the band gap versus diameter. The orange is the root mean square difference between the finite values and the green curve, which is the bulk silicon, meaning infinite. So it's calculated with the same parameters. So it goes down as a function of diameter as well, but doesn't seem to go to zero, which I'm curious about. Yeah. So we also ran, as I mentioned, the system that's twice as large, around 1 million electrons. We didn't get to full convergence for that calculation. Do I have anything? Okay. We were able to do this up to 2 CheFSI steps, but just in terms of the size of that calculation, for the 100K, we used 2,000 nodes. For the 200K, we used the whole Frontera machine, which is 8,000 nodes. So we used the system, the entire supercomputer, for about 26 hours, I believe, to be able to do 2 CheFSI steps. So this was a very interesting experience, running calculations on a full supercomputer with thousands of nodes. All right, I think, yeah, that's about it. For summary, as I mentioned, real space methods are powerful. We can simulate tens of thousands of atoms straightforwardly. So there are about 3 main thrusts in this research that I am interested in. One is pushing computational science forward and promoting this method in the community. So in our work, we studied scaling and performance. So this is of interest to computational scientists. The second one is investigating fundamental questions. As I mentioned, how do these bulk properties arise in real space? For example, I would like a student to analyze the data that I have of terabytes of wave functions. So these calculations produced a lot of data, and we can see the evolution of symmetry properties of wave functions, which I would like to study. Emergence of K-space features, as I mentioned, in real space. And then we have a lot of applications. For example, quantum dots, as I mentioned, is what I focused on in this study. They have a lot of uses. They're used in quantum computing, photovoltaics, photodetectors, LEDs. We can study optics of nanocrystals, in finite crystals of diamond, for example. These nitrogen vacancy centers can be created, which can be used as quantum sensors. They're also used as spin qubits in these systems. So there's a huge interest in these systems, which now we can calculate more directly with space. What else? Oh, and with large systems, we're able to simulate thousands of atoms, for example. This is a work that I started earlier at UC Berkeley with experimentalists, biophysicists, working on DNA sequencing with nanopores in 2-dimensional materials. we're able to see what happens to the electronic states around the DNA as DNA moves up or down. To summarize, density functional theory meets Dirac's challenge of finding practical methods of quantum mechanics. We implemented a real space pseudopotential DFT technique using Chebyshev-filtered subspace iteration. We implemented space filling curves, spectrum slicing, and then we solved the Kohn-Sham equations for over 100,000 atoms. We went up to 200,000 atoms even. And as I mentioned, there are many possibilities and fundamental understanding and application. So I'd like to get some students and collaborators to explore some of these areas. Thank you very much for your attention.
If you have a slide with quantum computer on it, did you actually have a physical quantum computer that you ran the computation on?
Not a quantum computer, no. I guess I maybe mentioned quantum computing. Yeah, so these systems are useful in quantum computing, but the computation itself is done on classical computers. It's actually interesting you mentioned quantum computing. There's a lot of work in using quantum computers to solve the quantum many-body problem directly without these methods. But that's a kind of a fantastical approach at the moment. It's very theoretical. But maybe in the future, rather than having to use DFT, we will run the simulation of the quantum computer that will do the many-body problem for us.
Yeah, that's going to make IBM and all the other companies happy.
Yeah, yeah, no, they're working on that.
They're going to laugh all the way to the quantum bank.
For us non-physicists, can you give us some idea of what you lose by, number one, neglecting all those electrons, and number two, cutting off the empty states? I mean, what do you expect that does to the fidelity of your solution?
So neglecting the electrons in the core, right? Yeah, so that's the pseudopotential method, which has matured in the past few decades. I mean, it's been around since the 70s. There's a whole industry of researchers developing pseudopotentials. So there are lots of tests that are run with pseudopotentials that they reproduce the physical properties while excluding the core electrons or folding them into the ion. So that's a good question, and it's something we take very seriously, and we test our pseudopotentials.
Well, I'm just sort of wondering qualitatively what do they?
These states that
we're in terms of fidelity.
Yeah, these states that we're interested in. Let me show you the plot of these states again. So the states that are ignored are all the way over here. And usually what is important in processes that we're interested in happens around zero, around the Fermi energy. So it is very rare that something at -30 eV has an impact in material properties or chemical properties. So we were safe to fold those into the
Okay. And then on the other side, where you
on the other side, yeah. So
states?
it is not computationally too costly to include more states that are empty. There is nothing terribly hard about including more empty states, and we do include a lot of empty states if we are interested in optics, for example.
Oh, okay.
So that
Because they tend to be occupied more.
yeah. So in optics, we're interested in excited states, how electrons jump from the ground state to excited states, and then photons and so on. So in this study, I was not interested in optics, but if I were, I would include states up to maybe 10 eV or so, and that would increase the computational cost. But there's nothing fundamentally hard about that. Yeah.
So, a question about the scaling, because I think at one point you mentioned it's dominated by some quadratic and cubic scaling steps, but
Yeah.
I wonder, because the systems are so large and commonly people do like a linear scaling method
Right.
to handle these kind of large scale systems. So what is the formal scaling of your method in the end?
Yeah. So the density functional theory scaling is n cubed. Yeah. So it's true for our method as well.
It's also cube.
Yeah, we're just trying to find ways to reduce the coefficient in front of the n cubed. Yeah, n cubed is inevitable.
Okay.
But we're trying to speed it up nonetheless. There is something called linear scaling DFT, but that has extra parameters that are somewhat empirical that need to be studied and optimized for a given system. So it's not actually very preferred in the field. People are working on linear DFT, but this DFT method, the Kohn Sham DFT, is first principles. So there's no empirical component to it. You can give it any atomic configuration you like and start calculating.
Typically, people think like the diagonalized Hamiltonian matrix is a cubic scaling step.
Yeah.
But here, do you need to do that, or you use
Yeah.
Use QR factorization.
Yeah,
That's just order in cube.
yeah, ordinary cube.
Oh, that's, yeah, if the n-cube method can handle these large systems, that's very impressive, I think.
Yeah.
Yeah, another question is, does the methods apply to like metallic systems?
Yeah.
Yes.
Yeah. Metallic systems just as well. Yeah. For metallic systems, what we introduce is some kind of Fermi-Dirac statistics around the Fermi level, because now you're going to have you're going to have empty and filled states right neighboring each other. We're still able to do this at 0 Kelvin. So the statistics is going to be a step function, but that hurts the convergence process. So we get a lot of non-convergence. So we introduce a smearing, and that tends to solve that problem. Yes.
Yes, I was wondering, so since you're producing terabytes of wave function data, do you use that, or is there any potential for using that to train the machine learning models to design new materials?
Yeah. I mean,
You talked about the silicons that probably related to.
That's interesting. I'm interested in analyzing the wave functions themselves for certain properties, some symmetry property, but as a data set for machine learning, I'd be happy to chat to see if we can come up with an idea. But usually we don't have terabytes of data in this field, so it's an interesting situation to think about.
So your method is helpful in reducing the number of computations. So do you think in the future there's going to be ground for maybe the startups to use maybe cloud computing, HPC, to come up with new methods for material design.
Yeah, no, I'm also interested in potentially exploring, drug design.
Yes.
Here, normally, this type of first principles method was limited to hundreds of atoms. So if you go beyond 1,000 atoms, it's non-practical. But now that it's becoming practical for larger systems, I'm interested in biomolecules and.
We have someone on the chat asking, can this be applied to an amorphous polymer? Sorry.
If we have a finite system like a polymer, a big molecule, there's no problem applying this method. But if you want to study an infinite amorphous crystal, which we also do, but if we want to do that, we usually define a large enough unit cell and then repeat that to approximate the amorphous behavior. So, but certainly people look at it, and as I mentioned, I'm interested in bio application as well. So,
What software programming language is all of that?
Sim Fortran. Yeah. Yes. I get some thumbs up.
By the way, we are developing a Fortran version of the Mon library.
Okay. Yeah. I'm wondering if we can use that. Yeah. Yeah.
So do these repeated cells, are they supposed to correspond to like grains, like in, say, in polysilicon?
Yeah. So you could have.
I mean, like,
Yeah.
those vary, right? And there's statistics.
So modeling amorphous systems theoretically is an interesting field. So I haven't worked on that myself very much, but for example, in the K-space methods, people still calculate these kinds of finite systems, but they leave a huge amount of vacuum between the copies. But that still causes issues because Coulomb interaction is long range, so you can have these artificial copies affecting each other and interacting with each other. So it's periodic versus not periodic is always an issue. So another advantage of real space is you can define a spherical domain, and it's finite by definition. So you can do your finite calculation. You don't have to worry about vacuum and copies and stuff.
On that note, we're going to thank our speaker.